locations, and trebuchets are also the most efficient catapults. There are 4 types of trebuchets, and these include swinging counterweight on a floating frame, swinging counterweights on a fixed frame, fixed counterweights on a floating frame, fixed counterweights on a fixed frame. Basically, a swinging counterweight on a floating frame is the most classic design, and the frame is floating, meaning that it is attached to a base that has wheels, so it's able to move around, hence the term floating, and it includes a counterweight hanging from one end of the throwing arm. So basket design allows for the weight to fall vertically, meaning it freely swings and adjusts to the fall, allowing for the projectile to be launched. Swinging counterweight on a fixed frame is another classic design, but the frame is fixed, meaning it's stationary, no wheels. And again, like the past slide, it includes a counterweight hanging from one end of the throwing arm, and as you can see right here, but it is not really visible with the picture that is shown, and the basket allows for the weight to fall vertically. On a fixed counterweight on a floating frame, it's a later design that was rediscovered, and the counterweight has no room for movement, meaning it is attached to the throwing arm. And when it was rediscovered, it showed promise because the projectile launched 30% farther with the wheels attached to the frame, as shown in the floating frame right here. For the fixed counterweight on a fixed frame, it's also later design as mentioned earlier, and the counterweight has no room for movement. And as you can see here, the frame has no wheels, meaning it is stationary. And it only allows for the movement of the arm, meaning there's no other movement allowed by the counterweight right here. And then this is the payload that would be launched once it drops. The benefits of choosing a swinging counterweight and fixed frame, which is what we chose for our design: it is a simple design and allows for more movement of the counterweight, meaning it is able to be adjusted accordingly, and it's efficient within our virtual simulations. And because of our virtual simulations, most of the values inputted were for a swinging counterweight on a fixed frame. The physics behind a catapult is essentially that stored energy from the counterweight is used to launch the projectile. So energy stored occurs through tensional force, torque, and gravitational force. The tensional force occurs between the string and the lever arm or the sling that's used. The torque occurs later on as described by the force applied to the string and the distance it would eventually travel because of the pivoting of the string on the pin needle and because of the pivoting that occurs by the counterweight, although it is less than the payload, and the gravitational force occurs by the payload. The trebuchet was the most efficient catapult design that, as mentioned earlier, and the energy of the falling counterweight is used to actually launch the projectile. So this is the basic design of what it should look like. You have a heavy counterweight over here, you have a sling, and you have the payload. The payload will be located, or the projectile will be located within a small pouch attached to the sling. You have your frame, you have your beams, and then this would be your arm that would be used. This would be the long arm, the short arm. And then, as you can see, once the counterweight drops, the payload is able to go from here in a circle all the way over here, and the launch angle can be determined by the pin angle, which is positioned right here. So, continuing on the physics of a trebuchet, the counterweight is able to pivot around a much shorter distance than the payload end of the arm. As you can see right here, it only follows this distance, but the payload goes from here, stretched out here, all the way up in a circle, and launches as a projectile, meaning it has a much greater distance for pivoting. And the payload end of the arm reaches a much higher linear velocity than the counterweight end of the arm, and this is considered your mechanical advantage. And linear velocity is the change in position of an object traveling in a straight path. As mentioned earlier, the string is pulled all the way over here, and as it travels this way, it is traveling with linear velocity because of the linear path used. And the payload reaches a high launch velocity, meaning a greater angular velocity. And angular velocity is considered the rate of the angular displacement over time, meaning it's moving along a circular path. And as mentioned earlier, it is traveling this way in the circular path, which means there is angular velocity as it prepares to be launched as a projectile. The counterweight pivots around a much shorter distance, as mentioned also earlier. Its weight must be much greater than the weight of the payload because of the fact that it travels a much shorter distance. It has to be heavier in order to do so. Increasing the mass of the counterweight beyond a certain point will not be efficient because the speed of the counterweight is all based on free fall speed and using gravitational force. The sling releases and the payload is launched within this picture, as you can see, and the payload is launched at a release angle, which is calculated through the pin angle. Sling releases when a certain angle is reached, as mentioned earlier, can be calculated with the pin angle, and the ring, which is connected to the sling and loops around the pin for support, slips off the pin, and the payload is launched So as it travels along the linear path here and circles around here, it reaches a certain velocity in order for it to allow to slip off the pin right here and allow for the projectile to be launched. The release angle can be adjusted by changing the pin angle, and for greater pin angle, the release angle must increase, and for smaller pin angle, the release angle must decrease. The physics of a trebuchet is continued, and as the arm rotates clockwise, the payload increases. The payload experiences centripetal acceleration, which causes the payload and the string on the sling to move outwards away from the trebuchet. And centripetal acceleration can be defined as an object moving in a circular path with a constant angular velocity with respect to a tangential speed, which is constant. The direction of the tangential speed of the velocity vector changes as the object moves along the path, causing the acceleration to occur. Torque is experienced also within the trebuchet because of the unbalanced weights between the counterweight and the projectile weight. Torque can be described as the twisting force causing a rotation, and with the applied force on either end of the arm, on the long arm and the short arm, with the counterweight falling and it pivoting while the payload or the sling is pulled, allowing for it to pivot upon the pin. Torque is occurring, and torque is defined as the amount of force applied multiplied by the distance it's applied to. So as you can see here, while pulling it over here, allowing for torque to occur when up here as it twists and moves off of the pin, the distance traveled by the projectile it factors into the torque of the trebuchet. Projectile motion, or the object or projectile thrown near the Earth's surface, moves along a curved path. This can be seen by the payload or the projectile after the trebuchet experiences the circular path and the linear path traveled. It travels along a curved or parabolic path, which is projectile motion, and it is only under the influence of gravity alone. There is no applied force, there is no tensional force. It travels through the air with only gravitational force. And in this case, air resistance is neglected, but within our case of the trebuchet, air resistance cannot be neglected because there is a wind speed and is not in a perfect simulation. In order to optimize the trebuchet for distance, the height of the axle will be placed above the platform of the trebuchet, meaning having a larger distance between the axle and the base of the trebuchet allows for the throwing arm to be placed higher up, increasing the distance it can travel when released, and the further it travels, it can accelerate more, which causes the tip speed of the throwing arm to be greater. Having a 5-to-1 throwing arm to long arm ratio, long arm to a short arm ratio is ideal for it to have a greater distance for the trebuchet, for the projectile to travel. Having the counterweight of 133-to-1 for the so counterweight to projectile weight ratio is also optimum ideal, and these were obtained through research conducted earlier, based on perfecting the distance traveled by the projectile. Lighter weight for the throwing arm, so meaning keeping the throwing arm tapered, having a lighter tip while the short arm is stout and strong, allows for also a optimum distance traveled by the projectile. Having a uniform weight may not be ideal. For hitting the castle, using longer length strings or slings, generally the length is 80% of the throwing arm, is also ideal, and having a lower angle of release is ideal. In our case, our angle of release wasn't exactly low. It was 90 degrees, but again, because of outside factors which could have affected our trebuchet, it was able to travel the longer distance. Conservation of energy can be discussed earlier with the energy used to describe how our catapult worked. The conservation of energy states that the total energy of the trebuchet is conserved throughout the entire process, meaning the potential energy described when the trebuchet is, when the sling currently here is pulled over here, it would have the greatest amount of potential energy, while traveling here, it would have the greatest amount of kinetic energy, and this would be conserved throughout the entire process and the entire movement of the trebuchet. As you can see here, the potential energy at the top of the counterweight right here would be the greatest, while dropping it would be the least. But again, potential energy can be converted to kinetic energy as it falls, and this is conserved, and it would equal the same total amount of energy. And the sling, when pulled this way, would have a smaller amount of potential energy, but as it travels here, the kinetic energy, potential energy changes and shifts, but never changes to a certain degree where the total amount of energy changes through the time and process of the trebuchet. And in our design, it appeared that in our design while testing and during the calculations, it appeared our design was the most efficient because it traveled the longest and it was able to travel a certain distance while also being able to hit a certain target through accuracy. So it could travel both long and short distances, and it appeared a large amount of energy was not used or lost. Instead, energy was conserved, so the trebuchet was able to work efficiently and accurately.
We built a trebuchet with the goal of achieving both maximum range and maximum accuracy.
After determining what trebuchet we would build, a swinging counterweight on a fixed frame, we used a virtual trebuchet simulator to determine our simulated results, how far it would travel and what time, and the release velocity. The inputted values we put in was length of the short arm, length of the long arm, length of our string or sling, length of the weight, the height of your pivot, which as you can see with the picture would be from the base to the top of the lever arm or the middle between the short arm and the length of the long arm. We are able to also put in a uniform arm weight or a varied arm weight, and we're also able to put in the counterweight, which was 98.09 for our simulation, and our simulated length of the short arm is 1.75, and so on. For our projectile that was in the simulation, which was given to us, is a baseball, and it would be 0.328 pounds, with a diameter of 0.249 feet. As you can see with the simulation, the dimensions given to us are much larger than we are able to produce. Hence, our results show that the distance traveled would be 282 feet in 5 seconds, with a release velocity of 130 feet per second. This is clearly very difficult to attain, which is why our simulation results initially looked like this, with 0.45 feet for our length of our short arm and 2.25 feet for the length of the long arm. Although a bit difficult to make, we found that this might work, and with our simulation results, we're able to see a maximum distance of 50 feet in 2 seconds with a release velocity of 42 feet per second. Although a very large velocity, it's still attainable. And as you can see with the mass of the projectile, it was calculated to be 0.022046 with a diameter of 0.1 and 0.1 feet, and the mass of our arm would be 0.7 pounds, and our mass of our counterweight was 4 pounds. And again, as shown with the results, the distance is 50 feet. 50 feet. With our actual results that we obtained with the real dimensions of our trebuchet that was built, we found 0.33 feet for our length of a short arm, which translates to 4 inches, and 12 inches for the length of our long arm and length of the sling. The length of our weight is 0.667 feet, and the height of our pivot was 1.1667 feet, or 14 inches, and we used a mass of 1 pound for our arm. It equated to 1 pound, and the mass of our counterweight was 4 pounds, while the mass of our projectile was custom, and it was 0.0625 pounds, with a diameter of 1 inch, or 0.0833 feet. And our release angle was a degree of 70 degrees, and we did not account for a wind speed because, again, in our simulation, the wind speed has little effect on the outcome. And as you can see with our results, it would be 13 feet and 2 seconds approximately, and a release velocity of 26.973 feet per second. Although this does not actually show what will happen in our results and our testing, it shows what could happen, and because there are other factors that can go into how our trebuchet can perform while testing, this just provides us with what we're looking for in our design.
Here on the left is a scale drawing of the initial version of the trebuchet that we built, and on the right is a scale drawing of the final version of the trebuchet that we built. Both are of the scale 1/4 centimeter equals 1 centimeter. There are 5 main differences between the two versions. First, the slings are made of different materials in both. The initial version had a sewn cloth pouch, and the final version had a gaffer tape pouch. This pouch was much more sturdy and let go of the projectile much more easily, allowing it to travel further. The spacers, which kept the lever arm straight in both levers, were also made of different materials. Hot glue was used in the initial version, but when it dried, it was not uniform and did not quite keep the arm straight. Therefore, we switched to electrical tape wrapped around the axle several times, which, due to its uniform shape and straight edge, kept the arm straight quite nicely. Next, the axle of the original version of the trebuchet that we built was made with a knitting needle. However, as we were reminded, a knitting needle is hollow, and when the counterweight was added, it broke the knitting needle. For this reason, we needed a much more sturdy axle, and therefore chose to use a drill bit. Perhaps the most obvious difference between the two versions is the counterweight. The initial trebuchet that we built had a counterweight which was constructed of a small dumbbell within a Tupperware container, which was then chained to the lever arm. The final version had a box on an axle which was able to swing, and this box could be filled with various things to make it heavier. This was much more useful because we could adjust the counterweight by adding more or less aquarium rocks as we chose.
When building a trebuchet, the first step was to create a sturdy base, which had two vertical posts that were parallel and a hole that was level between them. This hole is for the axle. The lever arm would then be cut out, followed by the construction of the box, which would serve as the counterweight. The lever arm would be connected to the two vertical posts via the larger axle, and a smaller axle would be used to connect the counterweight box to the lever arm. Then the sling was constructed out of gaffer's tape, and the pin was inserted into the lever arm. Finally, these things were all connected. Test day. The goal, to hit the castle. The challenge, to figure out how much counterweight made this possible. Too much and the projectile would go too far. Too little. The projectile would barely move at all. In order to hit the castle, we had to get it just right. On the first trial, we got within 10% of the castle's range. By adding only 3 minuscule rocks, we were able to decrease that number to 0%. We then added as much counterweight as possible in order to achieve the greatest distance.
22!
On the day that we tested the trebuchets, it was windy. This wind altered the distance that projectiles were able to travel. In the future, the people launching should wait until there is no or minimal wind before launching in order to achieve the best results. Additionally, the distance that the sling is pulled back before launching each time is often different depending on the trial. In the future, there should be a way to mark how far the sling should be pulled in order to achieve more accurate results.
Notice at the top of the screen all relevant measurements from 5 trials of launching a projectile from the trebuchet jerk. First, find the average time by adding all 5 times and dividing by 5. Then use the same process to find the average displacement in the x direction. You can then use both of these values to find the initial velocity in the x direction by dividing the average displacement in the x direction by the average time. This will yield a velocity of 3.89 meters per second. You can then use this value to find the initial velocity of the projectile. To do so, divide the initial velocity in the x direction by the cosine of the launch angle of the projectile. This yields a value of 11.37 meters per second. To then find the potential energy, multiply the mass of the counterweight times the force of gravity times the displacement in the y direction, which is how the counterweight falls. This yields a value of 2.133 joules. Then find the kinetic energy by multiplying 1/2 times the mass of the projectile times the initial velocity squared. This will yield a value of 1.83 joules. To then find the percent efficiency, of which the general equation is output divided by input times 100, divide the value found for kinetic energy by the value found for potential energy, and then multiply by 100. This yields a value of 85.92% efficiency for the trebuchet by the name of jerk.
Our trebuchet surpassed all expectations in its performance. At a percent efficiency of 85.92, it is quite efficient. However, it did lose energy. This energy is most apparently lost due to the fact that the launch angle of our projectile is 70 degrees as opposed to the optimal 45 degrees. Therefore, our design could be improved by altering the angle of the pin so that instead of being at 70 degrees, it was at 45 degrees so that the launch angle would be as such, therefore increasing efficiency.